10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Good evening and welcome to the Digital Futures workshop, that's Tectonic Formation. Now this is more of a symposium really than a workshop. It's going to be a series of lectures and discussion around the work from the RMIT Architecture Tectonic Formation Lab. So I'm going to share my screen and talk through what the lab is, what sort of work we're doing, and then also there's going to be a series of presentations both today and also tomorrow discussing in depth the research that's happening in the lab. Okay. So today I'll give an overview of the lab and then I'll be followed by Mark Gibson, who will be talking about a series of generative design techniques, and then also Da-Sung Wang, who will be discussing the relationship between generative algorithms and machine learning, in particular reinforcement learning. So the Tectonic Formation Lab, it's a lab that was established about 7 or 8 years ago. At least that's when it began to emerge, and it's more recently been sort of renamed and rebranded as the Tectonic Formation Lab. But it's essentially a research group that's been developing research around algorithmic design and robotic fabrication. So we consider these as sort of key elements to innovating within tectonics. And so a lot of the work that I'll be discussing today is around, I guess, unusual or inventive tectonics that have been enabled by algorithmic design, computational design, and robotic fabrication. And a lot of the robotic fabrication that we're dealing with is around additive manufacturing. So I direct the lab. My name is Roland Snooks, and there's 8 full-time researchers in the lab, which is Nick Bao, Natalie Lima, Hassan Mohammed, Charlie Bowman, Wenqing Yang, Mark Gibson, and Da-Sung Wang. And so this is a combination of PhD candidates and faculty members here at RMIT Architecture. And each one has a very particular expertise. And so the way the lab is structured is that each researcher is exploring a particular topic, and then we often come together to then to explore this research in more detail through demonstrator projects. And so what I'll be doing today is describing those demonstrator projects. The lab is housed at RMIT University in Melbourne, and so it consists of a research space as well as a robotics laboratory. So as I said, there's several main parts to what we do. One is around algorithmic design. And so the algorithmic work that we undertake and the digital design processes that we developed are largely based on multi-agent algorithms. And so multi-agent algorithms is, I guess, it's a technique or series of techniques that I've been working on now for around 18 years. And these techniques are, they come from a branch of complexity theory known as swarm intelligence. And I term this approach behavioral formation. And it's an approach in which individual entities, we can call them agents, can be encoded with design intention. And it's through the interaction of these individual entities that some type of collective or emergent design intention arises from the system through a whole series of these smaller level interactions. And so this type of algorithm is often used to model or to understand complex behavior in collective systems such as flocks of birds, schools of fish, social insects. But I guess our interest in these systems is not so much in the capacity to model or simulate the real world, but instead our interest is to use these as a design tool. And one of our interests in this is being able to think about individual design intentions and reduce those to a series of vector-based behaviors that we can encode within agents. And designing this way is never a matter of saying it's a sequential process where you go through a series of steps, but instead it's a series of behaviors which all negotiate with each other in order to generate a sort of negotiated complex whole. These are the types of behaviors that we typically write. These are diagrams of those, And they're all geometric. So they're all looking at the way an agent responds to some sort of geometric stimulus, whether it's agents around them or some type of high level geometry. Often we think of multi-agent systems as modeling points. We're less interested in that and more interested in the way agency can be encoded into higher level geometries. So in this diagram, it talks about the way we can encode agency within strands or within networks, such as a mesh. And often we do that in terms of the vertices of the mesh. And Darshan will be talking about more of that later on this evening. And then an algorithm I'll talk about a lot today is the agent body algorithm. And so this is an algorithm or an algorithmic structure in which agency is encoded into a series of strands, and a body is made up of several of these strands. And each of the control points or agents on these strands makes decisions in terms of the way it responds to geometry around it. So on the one hand, you have an agent which is able to navigate through space. On the other hand, its body, which is a highly tectonic construct, is then able to connect to other elements. And we often do this in order to make continuous lines of structure or ornamental effects. Another interest in the lab is around machine learning and the relationship between machine learning and bottom-up generative processes. And part of our interest in this is based on a premise that multi-agent systems operate from the bottom level. So they're about the way design intention is encoded into a bottom-up system, which leads to higher level emergence. Whereas machine learning operates on recognizing patterns at the surface level. So it's almost a top-down approach. And we're interested in the way these two can come into some sort of correlation or some sort of dialogue, and we can start to think about the way design intention operates at a series of levels. This is something that Darshan will discuss in more detail. Another algorithmic concern we have is the indexicality of algorithms. And so we see this as a negative thing, the way algorithms can often be, or the result of an algorithm can be indexed back to its process. And I guess our concern with this is that often this leads to algorithmic design shifting from a speculative or experimental approach into one of mere selection. And I guess what I mean by that is that if you understand the relationship between an algorithmic process and the type of geometry that it creates, then in selecting that algorithm, you already have an a priori understanding of what it's going to create or what's possible. And so the design decision comes through the selection rather than the development or experimentation of the algorithm. Now, we think in many ways, multi-agent systems are a very open-ended algorithmic approach, and so it allows us to create algorithms that are less indexical. But a whole nother part of our research is about how do we undermine the algorithm in some way, or how do we put the algorithm into some type of relationship with other processes so it's forced to respond and blur its indexicality. And so something that Mark Gibson will be talking about in detail this evening is this notion of painterly formation, or the way that we go back and forth between gestural operations and algorithmic operations. So it's the relationship, I guess, between gesture and self-organization. And it's something that we work on with our students as well. So if algorithmic design and digital design are key parts of our lab's research, the other half of our research is really around robotics. When we first established the lab and the facilities around 7 or 8 years ago, we explored a whole series of different robotic processes. But as we've developed our research, we've narrowed it down largely into additive manufacturing. And part of this has got to do with processes such as metal printing. Some of these have got to do with the notion of slow robotics, or the way a robot can interact with the growth of biological materials. This is something that Natalie Alima will be talking about in more detail tomorrow. But probably the key part of our research with additive manufacturing is around 3D printing of polymers. So this is something we've been now working on for around 6 years. And key to that is, how do we scale this up, and how do we overcome a whole set of building codes and fire codes and regulatory issues in order that this can become a serious part of architecture. So this is not about 3D printing for prototyping, but it's actually about 3D printing building parts. So this is this print is one of 10 prints that the lab produced 4 years ago as part of a permanent building section. So as a part of a wall that was built at the Sensi Lab. And so for us, that was a milestone in getting these projects out of the lab and getting them into real built projects, which had to overcome building codes, fire codes, etc. So these two parts of our research come together to do what I guess is the most important part of our work and the thing that we're most passionate about, which is innovating in terms of tectonics. And so for us, that often means looking at multiple materials or the way different systems come together. And a key concern is about the compression of tectonic hierarchies. So we're interested in the way that we can compress surface structure, ornament, sometimes surfaces, all into a cohesive whole. Something which is irreducible, can't be separated out. And we're interested in what are the architectural implications of designing through that type of logic. And a lot of this work is about embedding structure and surface and the relationship between those two. So for the rest of this presentation, what I'm going to describe is a series of prototypes, which almost all of them use an agent body logic and lead towards a process that we describe as sacrificial formwork. And this is really, I guess, the history of the lab in many ways, and it's the way in which we come together as a team and collaborate on given projects. And each of the researchers brings their specific expertise to a project. But it really starts with this image, and this is, I guess, an image that was produced in my practice just before the lab was established back in 2012. And it was part of a larger project we were doing. It was part of a train station. And we're making a series of these types of geometry, which we were proposing at an architectural scale. And I guess in doing this type of work, we began to realize that we'd pushed the limits algorithmically and in terms of digital design of what could be fabricated, what could be produced. We realized that these types of projects were no longer possible within the current production or construction paradigm. We realized that in order to bring these things into the real world, to bring them into a material, we either had to change the way we were designing them and simplify them and allow them to be constructed through the current construction paradigm, or we needed to undertake serious research into how we might change the way we build. And this is obviously then became the foundation for the lab. How do we start to use innovative techniques such as robotics and additive manufacturing in order to start to realize some of these complex forms, structures, and ornament, and to begin to think about those holistically in terms of the tectonics that they create. Now, in doing this, it's not simply an attempt to try and build these original digital sketches, but it's very much looking at the way these digital tools come into some sort of correspondence or feedback with modes of production, with robotics, with 3D printing, and how each begins to affect the other. And so the history of the lab has really been about how we attempt to build these complex geometries, how that causes certain innovation in robotics and construction. But then those innovations and those tools then have a meaningful impact on the things that we design. The constraints of those tools get built back into the logic of our design processes. So in a way, these two have a symbiotic relationship between design intention and the robotic tools that we use. When we first began looking at this, and this is really just at the time we're establishing the lab, it was we're looking at fiber composites, and there was a sort of at that time a renewed interest in fiber composites that was coming through people like Greg Lin and later Akim Menges, and we were looking at fiber composites as a way of embedding at a very small scale the type of agent-based geometries that we're working on, and whether those were ornamental or a larger scale that became structural and expressive. We're interested in the way the individual strands from our agent-based strand models could be reified within these types of structures at a series of different scales. But it was really with this project that we started to try and bring some of these ideas around tectonics and compression of hierarchies together. And so this was a prototype built in 2013, and it's a relatively small prototype. It's about 2.5 meters tall, but it's made from a very thin material. So it's made from fiberglass. It's less than 1 millimeter thick, about 0.85 millimeter thick. But through the compression of its surface, structural and ornamental systems, it creates something that's incredibly rigid. So the generative algorithm for this project is something we describe as a manifold swarm. And so it's where we start with a cloud of agents. And through the interaction of these agents, they begin to make manifold or coherent surfaces. Each agent body then connects with its neighboring agent bodies to make these continuous lines of structure and ornamental conditions. These agent bodies, in terms of fabrication, we cast them from polyurethane foam. And so in the end, we had 3 different agent body types, which you can see here. So 3 different molds. We cast these flexible polyurethane bodies, which were then laminated within fiberglass composite. So this is the process of making the mold, which is quite a sort of time-consuming process where we milled a whole series of parts, which then get assembled together, coated in resin. Several layers of fiberglass fabric are laid up on that mold, and you can begin to see towards the bottom of this image the way some of those agent bodies, the imprint of the agent bodies, are milled into the mold. So this becomes a way of locating them as we're fabricating, and also enabling that the surface to, I guess, have its articulation on both sides of the surface in 3 dimensions. More fiberglass was then laid over those, and then we use a process known as vacuum infusion, which we cover it with a vacuum bag, and we draw resin through under vacuum, which gives a very efficient composite. As I said, sort of less than 1 millimeter thick. Once that's done, we remove the mold, and I guess this was, in doing this project, it was sort of potentially like a sort of sad moment in the project. We sort of agonized over and carefully crafted this mold, which is the same size as the project, which of course we then hack apart and throw away. And I guess by doing this, we realized this is an incredibly wasteful process, and also a very inefficient process. And so it's a process that makes sense when you have repetition. It makes sense when you're making boat hulls or something which is in serial production. But for the type of one-off or highly customized bespoke architecture we're interested in, this represents a problem. And a lot of our work has been to overcome this problem of the mold. When you look at the detail, this is where we can discuss the way the structural system works. So these foam bodies, which are made from flexible polyurethane foam, they're very weak, they're very flexible. And also the fiberglass is incredibly thin and flexible at that scale. But when you put them together, they become rigid. And they gain their rigidity partly from the corrugation that's generated from the agent body, and partly from its structural depth. So the agent body, it's only about 10 or 12 millimeters thick, but that's significantly thicker than the 0.85 mil of the surface. So this actually creates a structural depth to the project, and this is why the limbs of the agent body need to connect to each other in order that this structural depth becomes continuous. The other way strength is generated is through the geometry of the overall form. So the geometry is, of course, has quite a lot of double curvature, and so in the end, this is a project in which its strength comes about through its geometry rather than through its material. I mean, its materials are flexible, but in the end, it becomes highly rigid. We were asked by the Design Hub Gallery to scale up that process and to create an installation for an exhibition that was called The Future Is Here. And it was an exhibition that originally came from the Design Museum in London, which was looking at the implications of additive manufacturing and advanced manufacturing in architecture, design, and the arts. And so we were asked to try and create an exhibition surface, which could also become an exhibit in itself. And so in many ways, that's what this piece is. It's it's part table, but then it creates a space where we're exhibiting, I guess, the architectural implications of these technologies embedded in the surface. So it's significantly larger than the last project. The last project was about 7 square meters. This is closer to 70 square meters. And in doing so, we realized we couldn't use the same logic. We couldn't mill an entire mold from foam for the project, nor could we rely on a certain type of craft-based approach where we individually placed each of the agent bodies carefully within the mold. We needed something that could scale up and become more industrial and be built by an industry partner. So this was really a project that was partly built at RMIT, partly built in by a boat builder. And it has two levels of agent-based inlay. And so you can see the larger inlay is an agent body network, which is milled from foam, and the smaller network is extruded from silicon. Each of these networks are responding to the structural imperatives of the project. So this is a diagram that describes the bending moments of the underlying surfaces. Now, without any inlay, this is only a 3 millimeter thick surface. The largest wings would deflect by about 1 meter. So in other words, there'd be catastrophic deflection in the project. But instead, this is resisted by the agent body inlay. And so these agent bodies are responding to the bending moments in terms of orientating the bodies and orientating their limbs and the way they connect their limbs in the direction of the bending moments in order to resist that. They're also scaling based on the deflection in order to create the necessary structural depth to resist deflection and bending. Those were milled from foam in quite a traditional way. So this is using robotic 5-axis milling. And it was quite a tedious process. We had to mill a jig, then we had to mill the back side of the part, then we had to mill the front side of the part. And I guess by doing this process, we began to realize that this has certain limitations. This is a process which, although undertaken by a machine, is incredibly machine intensive. It used a lot of robot time. The smaller part of the inlay was much simpler process. We built a bespoke extruder for silicon and extruded silicon onto a two-dimensional surface, onto a very fine fabric, which then got inlaid into the composite. The mold for the project, in the end, we used a reusable mold. So an idea that instead of trying to mill a mold for the entire project, we made one mold that could be reused to make 5 different parts, as well as several flat parts that come together to make the project. So we needed something that was more robust. So we milled parts of the project, the double curvature parts from MDF, using robots and 3-axis gantries. And then another part of it is built by a carpenter. So in many ways, this it sort of becomes a small architectural project in itself, the mold. You can see here, this is where we use one-to-one paper templates in order to position each of the elements. And so you can see Cam there is laying down some of the foam inlays, which then get laminated into the composite. This was done by boat builders, I guess through what is now a traditional composite boat building technique. Those then are trimmed down before being installed initially in the design hub at RMIT University in Melbourne. This is the largest piece going up on the wall. And the parts have two very different sides to the surface. So on the right, you can see it's a very smooth surface, which is the surface of the mold. On the other side, it's a highly articulated surface. And this allows, I guess, repeating mold without repeating pattern. So the mold surface stays smooth, whereas the non-mold side enables each part to have to be bespoke, to have a sort of a different pattern. This was then re-exhibited in 2015 in China at the Shanghai Biennale. Due to the complexity of that project, we began looking at other ways of making this type of geometry. And one of those techniques was using flat sheet material. So this was a small exhibition that we did in New Zealand, in Wellington, where we were laser cutting metal sheets. In this case, it was steel. And then the way those steel parts then riveted together generated its double curvature. So we wrote an algorithm that could take one of these agent body networks, could step through it, work out how to unroll the largest pieces that could be unrolled to flat parts. And then through riveting those together, they then it finds its own form. Now, we then wanted to be able to extend that process so we could create something which had surface, but also something that used the composite materials we've been working with. And so this was the next iteration of that. And this was in 2015 at the Tallinn Architecture Biennale in Estonia. This is where we took laser cut carbon fiber sheets in a very similar way. And instead of riveting those sheets together, we were gluing them together. And through gluing, they then generated their own double curvature. Once the skeleton had found its form, we then infused a very, very thin layer of glass fiber on either side of that. So in the end, the glass fiber in this project is only 1/4 millimeter thick, but provides all the shear strength for it, while the carbon fiber skeleton provides the primary structure. And in many ways, this was a breakthrough, I guess, in this quest to try and do without the mold in the work that we're doing. But it also had another problem. It made something which was very, very thin. And a lot of our initial studies was looking at these sort of thick fibrous mass geometries where they were somewhere between a sort of surface, lattice, and volume. But this line of inquiry really kind of compressed it down to a very flat surface, a very thin surface, I should say. So we needed another way of progressing this work. So simultaneously, we were also working on a strategy where we would try and build each member of the agent body as an individual line, in this case as a brass rod. So this was a project, again in 2015, where we're using robotic rod bending in order to try and generate a thick fibrous lattice, but in this time without a surface. One important aspect of this project for us was that the underlying generative algorithms that we're using are inherently highly volatile. They're wild algorithms, and they make complex structures which are very hard to post-rationalize. So what we needed to do is to understand exactly how the robots would bend these parts, what the limitations were, how far they could bend, what the sequence of bends they could do before the rod would hit itself, how far apart those bends could be, and then program all those constraints into the generative algorithm. And the ambition of this was that then the generative algorithm would be able to create these wild structures, all within the limitations of what is possible in terms of fabrication. And this is a key concern that we have. We're interested in this idea that the constraints of building science, and whether those are around structure or around process of construction, don't derive the architecture, but inherently condition the architecture. And so what I mean by that is that the projects are always driven by a set of design intention, which is encoded into our algorithmic processes. But we want to always encode the underlying logic of structure and fabrication into these projects so that we don't end up post-rationalizing or simplifying the complexity of these projects as we try and resolve them. I should say with that project, it was very rapid to fabricate. We were able to fabricate all the 270 brass rods in a single day. The problem then became one of assembly. It then took 5 people, 5 days to assemble and to weld this project together. And so we realized in a way we were really optimizing the wrong thing. We're optimizing fabrication, whereas we probably should have been optimizing assembly. We also tested this at a larger scale. This was actually at a previous Digital Futures event. I believe this was 2016 at Tonji, where we're using Tonji facilities to using a couple of larger robots with larger rods. In this case, we were bending aluminium in order to make a small pavilion. But our ambitions for this, of course, is not to make things which are exhibited in galleries or small pavilions. We want to try and take this work up to a larger architectural scale and in these types of projects. So those two parallel streams of inquiry in terms of how do you build the agent body, each had the opposite problem. So one became very thin and it had a surface, but it sort of lost its thick fibrous mass that we had this ambition to create. And the other one had the lattice, but was incapable of being surfaced. And so it was really this project, which was an attempt to try and bring those two, in many ways, diametrically opposed logics together. And we realized in order to be able to do this type of project, we needed to flip our logic. So instead of this idea of building the agent body and then working out how to skin it, we flipped the logic and started to think about how could we create skins which we could then cast agent bodies back into. So in this project, it's a pavilion. It's a competition entry for the National Gallery of Victoria. We're looking at the way these surfaces will begin to delaminate and create a sort of a thicker, more turbulent mass beneath it. And so it shifts here from surface to lattice as it goes towards the interior. And this was when we really started to take additive manufacturing seriously in terms of plastics for building construction. So I guess up to this point, we were skeptical about the use of plastics in buildings in terms of 3D printing. A part of our skepticism was about the speed of printing, perhaps also about material robustness. But as we started to experiment with it more, we realized we could actually print relatively quickly using pellet-based extruders mounted on robots. So this is now from about 5 or 6 years ago. We're looking at this, and we started to print these thin skins, which we then had a series of conduits within, which enabled us to cast the agent bodies back into. And so in this case, we're casting high strength concrete back into, sort of fiber reinforced concrete, as a way of trying to make these highly intricate concrete structural networks. You can see this is one of the prototypes with the concrete core. It's cast within the layers of plastic. Another detail of that. This is something we tested through a series of architectural and art projects. This is a shortlisting for an art installation or a public art project in Melbourne. But it was really the NGV who then came back to us to give us an opportunity to scale this up to something, I guess, more at an architectural scale. I mean, it's an installation, of course, it's not a building, but it's about 6 meters tall. It was installed in the Great Hall of the National Gallery of Victoria here in Melbourne. And it was an attempt to really show, I guess, how this might scale. But in doing so, we also had a whole series of limitations. This project was done incredibly quickly. We had about 3 months from the start of design to the installation of the project. And so we had to develop a whole series of strategies for de-risking a project like this. The project was a collaboration with the sound artist Philip Smartsis. So Philip takes all these amazing recordings from places such as the Antarctic, and then recomposes it into sound art. And so what we were tasked with doing was to try and create a space which captured some of the atmospheric qualities and some of the sort of the characteristics or affects of the location where these sounds were recorded. So we're trying to create something which was ice-like and had a certain atmospheric ambience that was generated from that. And so we're looking at the reflection and refraction of light through 3D printed plastics. In this case, it's looking at PETG, and the way that contributed to creating a very specific atmosphere which changed between day and night within the space. We're also deliberately trying to create something which was very sort of white and pure within the space, which was incredibly rich and colorful. And so this is a view looking up the tower to the Leonard French stained glass ceiling, and sort of using our project to frame this amazing ceiling. So the project is fabricated from 70, a sort of swarm of 70 3D printed panels. Each panel is about 1.7, 1.8 meters tall. And they're printed relatively quickly. They're sort of printed in about 4 hours. So the project was really designed to optimize things like printing time. So this limited the draft angles we could use, it limited some of the geometries we were able to produce in order that we could fabricate a lot of these very quickly on a single print cell. In creating this series of panels, we were creating, I guess, a family of similar forms. And so each panel was a parametric model, whereas its individual articulation, the sort of rippling, the corrugation on the surface, the sort of folding, came about through an algorithm that operated at the higher level. So this was an algorithm that was creating unique patterning across each panel, but generated at the global scale of the project. Each of these panels was printed with a different translucency. So the project ranges from panels which are sort of highly transparent and very glossy through to much frostier panels. And between these panels, an agent-based or agent body-based steel structural network is woven between the panels. And so the idea is that the structure is not on one side or the other of the project. It's not a steel structure which is then clad with plastic. Instead, it's a sort of intertwined plastic and steel, almost a composite. However, we're also critical of this. We feel that in many ways, these two elements, structure and surface, became too separated in this project. And it's something we've attempted to address in our later work. So this is the unrolled structure. So you can see the agent body network here. And this was done, as a lot of our projects are done, in collaboration with Bollinger Grumman, structural engineers who resolved this project. Our ambition at the start of the project was to create an all-plastic project, a project with a plastic structure and cast in place agent bodies. But due to the amount of time in this project, it was only a 3-month project, that simply wasn't possible. So we had to rely on sort of more traditional means of in this case, a folded steel structure. So these were laser cut pieces of steel, which were a CNC brake press folded to create the agent body structure. And these sit on top of a more conventionally produced base. So the base is fabricated from timber using 5-axis and 3-axis milling techniques. This then creates an amazing jigsaw puzzle of parts that had to be put together. The project was assembled on a very short schedule. We had a 3-day installation window at the museum, at the gallery. And so we had 70 unique panels. We had over 300 unique pieces of metal, of steel that had to be put together. And so instead of relying on drawings, we were looking at ways of using augmented reality. And I guess this is a few years back now. This is sort of, this is about 3.5 years ago. And just at the time when Hologram were establishing their business, and we were interested in using this technology as a way of removing drawings from the building site. Of course, this is something which is becoming more and more familiar now. And this is a short video which gives you some insight into the way the installation team would then look at the digital model, see what parts required, grab that part, put it into place where they could see that the holographic representation of that, and then these parts get mechanically fixed together. So this allowed this project to go up relatively quickly. And you can see here that the plastic and steel go together. So basically, steel and plastic are assembled as a single unit, which is then put in place. And so you can begin to see this fabrication. This is a short video which goes through the sort of time lapse of the installation. So the initial steel pieces are mechanically fixed to the base, and then from then on, each of the parts come up as a composite of steel and plastic. And so those 70 parts are assembled, as you can see, over a 3-day period. This was for an event at the NGV, which only was originally intended to run for 10 days. They had about 85,000 people come through in the first 10 days, and then the project was its lifespan was extended for about another month. As I said, our interest really is in innovating in tectonics, and I guess that project was a relatively conservative tectonic approach, where we had the steel structure and the plastic panels, which were separate. And at the same time, we were going through a series of other projects. We were looking at the way those things could come together and the way we could start to bring some of the painterly formation approaches into this work as well, such as this foyer project, or this project in Portugal, where we were looking at the way we could embed the steel structure in between the layers of plastic. And so, so this became a slightly more kind of cohesive approach. But that also threw up a whole lot of problems in terms of the way you separate the plastic parts and the way you make these sort of seamless connections. So we went back to this logic we had of casting the body within the 3D print. But instead of relying on high strength concrete, we started to look at much lighter weight fabrication approaches, and in particular, going back to our exploration of carbon fiber and fiber composites, and looking at the way we could infuse carbon fiber structures into these 3D printed assemblies. And so this became a catalyst for a research collaboration with the aerospace company Boeing. And so we've worked through with Boeing a series of projects in which we've explored different ways in which we can embed carbon fiber structure into a 3D printed mold. So in a way, these surfaces become this type of sacrificial formwork that I was discussing earlier. This idea that we no longer need a mold for the fiber composite, for the carbon fiber. Instead, what we can do is start to use the actual architectural print as as a type of permanent or sacrificial. So the first test of this was this project in China. This was in Shenzhen, so for the Shenzhen Biennale. And in this project, I guess it's a really key project for us because it brought together a lot of the research we're doing around this interaction between algorithmic self-organizing processes and more painted operations. It was an interest in bringing together structure and form, structure and surface into a kind of cohesive architectonic element that was irreducible. And also multi-material systems, bringing together composites with the additive manufacturing and 3D printing of plastics we're working on. So this project was printed in about 13 parts, which were then mechanically fixed together. Has several layers of printing. So it has the outer layer we describe as the skin, an inner layer of the agent bodies, and then a core, which is the carbon fiber conduits. And you see there's very deliberate blurring between the black agent bodies and the skin of the project. So these, at sometimes they laminate and come into focus, and other times they become more diffuse and they sort of blur into the background. These projects end up becoming as much about robotic fabrication as they are about craftsmanship. And so there's a whole series of post-production steps that happen after the 3D printing of these to make these a sort of viable construction technique. That project, one of the problems with that project were around the mechanical fixings, but also around the difficulty of accessing the carbon fiber skeleton at the center of the project. Since then, we've started to look at the way carbon fiber can be embedded into these 3D printed assemblages in different ways. This is a recent project from the lab where we're looking at the relationship between 3D printed skins, growing mycelium core material within it, and embedding fiber composite tensile elements on the exterior of the project. So this brings together the work we're collaborating on with Boeing that Hessam is working on, as well as the work that Natalie is working on in terms of biological growth within architecture. So the core of this is mycelium. So mycelium is the rootstock of mushrooms, and Natalie will talk more about this in more detail tomorrow. And we're using this partly to make a compressive core for the sandwich panel, but also as a way of making insulation. So there's a series of studies that went into this. And this is an attempt to try and make work towards making an entirely biodegradable sandwich panel. So a lot of the previous work I was showing is printing in virgin plastics, which we see as inherently problematic, but it's a sort of step to a whole series of other processes. So this project is printed in entirely recycled plastic, which will then using fiber reinforcing using flax fibers and natural fibers and bioresins to infuse those into place. And so the idea is that working towards making something that's biodegradable. Part of these studies is also printing in wood plastic composites or wood bioplastic composites. And so this is a combination of bioplastic and timber fibers, which enable a material that can be 3D printed, but it's also entirely biodegradable. And so I guess that's in many ways our ambition for this work, to try and either be able to print from recycled plastics or print from biodegradable plastics. The other innovation on this project is a shift of the composite fiber reinforcing from the sort of central skeleton onto the exterior. So this made it more accessible. It also put the tensile elements where they're inherently needed, which is always on the outer surface of a structure rather than on the internal part of it. So these were a series of conduits which were printed into the surface, which we then laid the fiber composites within. Okay, so that's taken me through a lot of the projects. The last projects I want to just briefly touch on before I hand over to Mark Gibson is a series of metal printed projects. And so this is something we've been working on for a while at different scales. And so early on, we're looking at these very intricate, highly detailed fibrous mass structures. and looking at the way we'd print those at an object scale. And so initially we're looking at the way you could print those in aluminium and titanium. And for example, this print is a relatively small object. It's about 600 millimeters across. This one's printed with a relatively large amount of support material, which is then removed. And each element is very fine. So the diameter of each of these elements is only about 0.4 of a millimeter across, and it's comprised of about 1.1 million agents which are interacting. So it's incredibly intricate, high resolution structure. It has a series of different qualities, a sort of phrase at the edges. Underneath the wings, it takes on a more turbulent, thicker characteristic. And as you zoom out, there's almost a flattening of that detail into its overall form and silhouette. So this is a small project that was what we describe as a retroactive form study. So it originated on the bridge design I showed earlier, and then was developed into this object, which was exhibited at the Centre Pompidou in Paris as part of the Code Le Monde exhibition. And this is an exhibition that was tracing the history of algorithmic procedures in art and design and architecture. So a sister project to this is this ceremonial mace, which was developed for RMIT University. And this really draws on the logic of the history of mace design, which is around these highly ornate objects. In this case, we were particularly interested in the relationship between that which is emergent and that which is directly drawn and modeled. And this is something that we really work on, I guess, more in the practice than in the lab. But a key aspect of the work is how do you relate things which are directly modeled to things which are allowed to emerge through generative processes. So at the head of the mace, it's a highly volatile generative self-organizing algorithm that generates the mass of this. But as you move down towards the handle, the geometry is highly constrained by something which has been directly drawn or modeled. And this enables two very different types of control. So one is a intention which is encoded into an algorithmic system, and the other one is a top-down type of control. This particular object was printed in 4 parts, and so it has a series of joints. So there's almost like pin joints, which then enable this, I guess, highly intricate lattice type structure, which sort of thickens at the edge. So you can see this is a section through the handle, and you can see where this fibrous network begins to compress onto the surface to make a sort of a handle that you can hold. Whereas lower down on the object, you can see the sort of more pure algorithmic fibrous quality of it. And these parts then get pinned together and welded together using a laser welding technique, which operates under a microscope. So it's actually a jewelry welding technique. So that project was printed in titanium. So, but I guess in doing those projects, they enable the intricacy of the architecture we're interested in and these types of thick fibrous mass, but of course is entirely unrealistic at the scale of architecture. I mean, this is something which is printed on an SLM printer, a selective laser melting printer from titanium. This mace took 10 days to print. So, and it's only 1.2 meters long. So it's not something that can be scaled up. However, since then, we've been working on ways in which we can begin to scale this up. And so we've begun to look at wire arc additive manufacturing, or WAM. And so this is a metal printing technique, which is using a MIG welder, which is mounted on a multi-axis robot. And because in MIG welding, the arc is made by the filament, the wire, which is fed through the welding torch. When that connects, it closes the arc and melts the wire. What it's effectively doing is feeding wire through the torch and laying down layer after layer of molten metal. So in many ways, this is a printing technique which is not dissimilar from the type of layer by layer plastic printing that we've been doing. But of course, it's made from a much more architectural material, something which has far more structural capacity. So this is an early project that we collaborated with Wollongong University on. And then this is some of the more recent work where we're beginning to refine the 3D printing parameters and to try and sort of refine those layers and get a sort of a higher quality of printing and higher control. So you can see in this prototype, This is, again, is an agent body, very similar to the agent bodies that were SLM printed in titanium. But instead of the diameter of these bodies being 0.4 millimeter, these are closer to 40 millimeters. So this is scaling that up by a scale of 100. And suddenly this then becomes a scale at which we can begin to consider 3D printing of metals within architecture. Another aspect of this is looking at the way we make a hybrid system, which is not directly just trying to print the whole project, but looking at the way we make a hybrid of folded sheet metal, so more traditionally fabricated metal. In this case, it's laser cut and CNC brake press folded, and WAM printing. So here we fold a piece of metal, then we print onto it. We then create several pieces of those, which then join together to make a, I guess, a complete part. This short video gives a sort of insight into the first installation, first prototype we attempted with that. So you can see here that the brake press folded metal is printed onto using this wire arc additive manufacturing approach. Each agent body here is then printed out of two components, which are then welded together to create the final object. Okay, so that brings the first presentation to an end, and I guess through that, what I was trying to do is to explain what the agenda and the ambitions of the lab are, and then explain how each of the work of each of our researchers comes together. It begins to be hybridized, begins to interact with other bits of research in order to be tested at these larger, what we describe as sort of demonstrator projects, these tectonic chunks, where we're trying to take the more pure research and then use it as a way of reimagining tectonics and how they can be rethought through computational design as well as robotics and additive manufacturing. Okay, with that, I'm going to hand over to Mark Gibson, who's going to talk about his research within the lab, which is looking at, I guess, form generation and the relationship between algorithmic processes and more direct painterly operations. So, Mark, over to you.
All right, I'll just share my screen. Okay. So my name's Mark Gibson. I'm an associate lecturer at RMIT, and my role within the Tectonic Formation Lab is in the development of tools and workflows for digital design and also resolution of fabrication processes. So as I'm sure you've seen in Roland's work, or Roland's presentation just before, we're really interested in the development of complex topologies. And this sort of intricacy operates on a number of scales, not only the larger sort of formal scale of the design of the project, but also on the fine-grained ornamental scale of the surface, and also in the cross-sectional sort of volumetric properties of the objects. So in terms of the layering of multiple aesthetics, but also functional qualities like structure and functional aesthetics. So with all of this layers of complexity, it obviously adds challenges to the sort of design process and resolution process. And so when I'm developing a series of tools, I come in either at the sort of early stage of a project or a late stage of the project, and I work collaboratively with the talented team at the Tectonic Formation Lab. And so this really is a process of moving back and forth between sort of existing tools that might already be there, and figuring out whether we need to optimize something just purely logistically to make it faster, or to invent a new tool or workflow to solve that problem. So as Roland was showing before, we're really interested in additive manufacturing, so 3D printing. And there's a series of challenges which are pretty commonly known. So dealing with things like draft angles and delamination from, again, extreme print angles. And this is, I guess, further exacerbated in our projects because we're dealing with not only highly detailed forms in terms of the sort of the mesh size, but the variance of the shapes themselves. And so these generally require multiple cut planes and offer up further challenges. So as part of this, I developed a piece of software which could help essentially run multiple draft angle analysis. So this is called Theta, and if you're interested, it's available for free on Food for Rhino. So what this allows you to do is essentially analyze a 3D form and run multiple draft angles without having to split the form. Because as part of the challenges in the office is we're dealing with a really large form that has to generally iterate quite rapidly with the design techniques we're using. And so having to split that becomes a hindrance in the project. And so you can see an example here on screen with that sort of workflow integrated. And generally the reason why we do this is because with our design process, we like to have control over the top-down sort of design properties as well as the algorithmic, and have a sort of an interaction between the two. Now on screen here, you can see we're operating on a fairly low resolution sub-D model of a bit of geometry, and we're roughing out to figure out the sort of parameters of what we're working with here. On top of this, we're visualizing what the higher resolution bit of geometry would look like when they're sort of connecting for a 3D printed form, whilst running the layers of draft angle analysis. So this is useful because we can flag potential errors before. Roland was speaking earlier about like building these into the algorithmic techniques where you would essentially have the bodies adjust themselves to avoid the draft angles. But generally we find with really complex projects, it's never going to holistically eliminate them. So being able to have a real-time sort of feedback and flag these issues, these minor issues early, becomes quite useful in the process. But beyond the sort of the practical nature of sort of developing tools for the office and sort of into the more speculative end, I'm really interested in the emergence of sort of complex topologies and sort of intricate forms that occurs when you start to combine the software, not only software, but algorithmic techniques, and particularly when they happen iteratively. One, because it starts to sort of create this idea of ambiguity in terms of where they've come from, and also sort of influence this idea of emergence, where you allow the process to sort of deliver the qualities that you're interested in. And so a key aspect of this is thinking about the indexicality of the tools that we're using in the office. And so quite a straightforward example of this is sort of when you're mesh modeling. So on screen, you can see a Maya model, which I've just sort of quickly modeled up. And so the actual topology of the form, the representation of the form, is defined by the actual mesh class that you're using. So the vertices, the edge segments, the faces, and the elements. And so it has, even though it still has quite a flexible range in terms of geometries that you can produce from it, it's still inherently tied back to that structure of the design tool itself. Likewise, when you're designing algorithmically, the actual process or the system that the algorithm is using is indexical back to that rule set. And so in the office, we're less so interested in the exact replication of a natural system. So for instance, like, lightning, where, an example of replication might be a pathfinding algorithm or a diffusion limited aggregation algorithm. And we're more interested in the development of bespoke tools, which are trying to achieve a specific sort of aesthetic or functional quality. So in the pursuit of this, we have developed a number of strategies to try and blur the lines between the indexicality of the algorithmic techniques and the top-down design techniques. And so one of the most straightforward sort of brute force techniques is iteration. So moving back and forth between software and allowing that entire process to run several times. So what you're seeing on screen right now is an earlier test where basically we would start off with a model, which was designed as a top-down piece. It was then fed through an algorithm where essentially a field ran over it. And this would do two things. One, it would crease the mesh, and two, it would distribute objects onto the mesh. From there, it was then brought into ZBrush, which is a sculpting application. And the geometry was remeshed and sculpted, and then sent back to the algorithm. And so this is looped through several times. Part of this technique also requires a sort of a communication between the software processes. So in this instance, it was using vertex color. So you can see where it's painted red, there was more activity from the algorithm versus sort of areas in blue. So it's this sort of top-down feedback where after you run the algorithm, you could resculpt, redistribute the colors, and then run it through again to sort of create this blending qualities. The next aspect of this process is really allowing the operation to occur at quite a high resolution. And so this is to allow the emergence of these qualities at a number of scales. One at the, obviously the larger scale, but also the very fine grained scale. And so it can allow this sort of cascading effects where it's difficult to identify where one part of the process ends or starts. So through the combination of these behaviors, we are really looking to generate a series of qualities or a taxonomy of qualities. And so what we've found, sort of a successful part of this is the sort of, particularly when we're using algorithms for multi-agent algorithms, dealing with sort of an aggregate of individual components, is allowing the process to remesh and recombine pieces. And you can see on screen, it's creating these sort of ridge lines or layers in these areas. And we describe this quality as a sort of a flaking quality, where you're getting near parallel pieces, which are starting to merge in and create these sort of complex topologies where you could look at a macroscopic scale or a fine grain scale. A real challenge with this workflow is dealing with the actual friction of this process. So the logistics of moving back and forth between software and keeping track of the decision making. So I developed a bit of software to sort of reduce this friction. And so if you're interested, it's also available for free on Food for Rhino. It's called Chameleon. And so what Chameleon is it's essentially a live link with ZBrush between Grasshopper and ZBrush. And it allows you to not only send geometry back and forth between applications, but also allow you to set up parametric loops. So you can set up a series of operations, which would typically require you to actually click through in ZBrush. So you can sort of set that up ahead of time. And so we use this in the office for sort of early stage testing, where we're just sort of moving back and forth between iterations, as well as in design studios to rapidly test different components and different sort of fine grain sort of outcomes, as you can see on screen here. So as I guess a further extent of this test, I was interested in this idea of seeing how much we could automate the painterly process. So in the previous iterations, it was mostly me manually sculpting the objects. And so I tried to strip back the amount of direct user control. And so what you're seeing on screen here is just an augmented reality interface. So this is going through Hologram. This is a base app. And I'm just controlling the control points of a spline. And from the spline, it's distributing objects and agents. And that's being sent through to ZBrush, which is running a series of operations and sending that back through to the augmented reality app for sort of visualization purposes. And so, at least with a lot of these early tests, the process was relatively linear in terms of the way the logic of the geometry works. So it was typically just obviously starting with a base mesh, and it was either a distribution of components on top and a layered distribution, which would sort of recursively grow, or it would be a sort of static bit of geometry, which is then folded and it's essentially looped through with that process. So I was interested in pursuing this aspect in a sort of more of a free topology, so allowing the topology to shift and adjust over time. And so we tackled this through sort of a mesh growth procedure using a common technique of half-edge mesh structure, allowing the sort of subdivision of a mesh. And the tendency with this process is to really pull from like natural systems or representation of natural systems of coral with differential growth. The aspect of this which we wanted to avoid was the trope of these self-similar sort of folding surfaces. But a interest of it, though, was the topological complexity that could start to emerge from the base of the rules. So it was more just an inspiration for the topological complexity rather than strictly the aesthetic. So what you're seeing on screen here was sort of a first application of this, where taking a mesh growth procedure, which would run almost in real time with an interaction with sculpting, where the mesh growth procedure would run for a number of iterations. It would then automatically be sent to ZBrush, where it would run a series of procedural operations. And from there, I would intervene and make adjustments to the detail of that surface. And then I would essentially send it back to the algorithm, where it would run for another further couple of iterations, and then I would intervene again. And so this occurred about 4 times for this initial test. And so I'll sort of unpack this logic over the next few slides. And it's sort of, the transition works both on sort of the technical sort of topology of the mesh, the sculpting, the analysis in real time of the geometry to sort of make adjustments to that mesh growth, and then also in the representation and materiality of this object, sort of carrying across an animation. So what you're seeing on screen here is the sort of mesh growth algorithm. And so this is using a very straightforward sort of mesh subdivision technique, where essentially as the mesh edges expand past a certain point, once the length of the edge gets too large, it would then add an additional vertices, so it'd subdivide the face. And that's how it's sort of iteratively grows and adds more details as it needs to. So as it's growing, it's considering its sort of local position in the world, as well as its neighboring agents. It's considering color intervention, so vertex colors which are drawn on the mesh, as well as analytics of the curvature of the geometry, normal direction, and draft angles, with very low influence from draft angles at this point. So once it ran for a few iterations, as I was mentioning before, it would be sent through to ZBrush. From there, I could either completely deform the geometry or adjust the details, so where the creases are happening. And this would also be to either smooth out areas where I wanted less detail or increase the level of detail in certain areas, sort of cause trouble for the algorithm, essentially. And right now, this is showing at a fine grain level of detail, but obviously you can push and pull the mesh around. A limitation to the workflow that I was dealing with is because I was trying to represent this as an animation of growth over time, I did not remesh the geometry. So I had a consistent vertex count so that it could remain continuous with the algorithm. So it sort of limited the, I guess, the hybridization of these forms that were present in previous iterations. And so on screen right now, you're seeing just layers of different analysis. So that was draft angles, sort of normal position. And then lastly is just the direct color painting from ZBrush. And you can see over time, the color is sort of fading in between different instances of me actually sculpting that color in place. And so as I would make adjustments, I would want the script to add in more detail in certain zones and reduce detail in others. And so this is, again, purely to create a sort of a fuzzy sort of interaction between the qualities that start to emerge in either end of the process. Now, as part of the sort of the analytics and the sort of top-down coloring, as a process to try and actually represent this sort of as a 3D render, but also thinking about the materiality and patterning on a surface level of detail, because we all want more detail in these projects, is thinking about how we could actually translate this and unroll it flat. And so I looked at a couple of different processes. So the first process is really post-process to the sort of formation of the object, and that's looking at something called a trivial per triangle unwrap. And it's a fairly simplistic approach where basically you unweld the geometry, unweld the mesh, and you translate the vertex color information from each point to a pixel on a screen, on a texture, flat 2D texture. And so the benefit is it's very straightforward to do this as a post process and translate, highly intricate forms. The drawback of this process is that it unwelds your mesh. And so when you then try and represent a fine grain level of detail, particularly with displacement or subsurface scattering materials, it will sort of explode your geometry and break it apart. So purely from a representation, it causes havoc. So I looked at a different technique to try and essentially map on a more designed unwrapping procedure. And so the challenge of this is the geometry is quite high resolution and topologically complex, which makes it very difficult to unroll in large pieces. You could obviously unroll it in lots of little strips. So to do this, at the initial stage, so before the geometry grows, I made a low resolution sort of offset of the object and unrolled it flat. From there, I took the high resolution bit of geometry and looked at the vertex positions relative to the low resolution face, and essentially translated or inherited the UVs from the low resolution object onto the high resolution object. And this is done by essentially interpolating the texture coordinates of the face and the relative position from the corners of those vertexes. And so this is done at the initial stage. And so once the object has inherited those qualities, as the mesh subdivides, it would then just interpolate essentially the texture coordinate from there. So as it grows, you don't have to recalculate or re-pull the UV coordinates from this. A drawback of this process is that the initial UV unwrap has to be very high resolution, sort of 10,000 pixels plus, so that you give it enough space to grow and add in a sort of a procedural or pattern-based detail at the level of the surface. So that brings us to the materiality, so the representation of it, and really tying this to the function of the algorithm and sort of the layers of that process. And so this was done as a multi-layer texture where the materials themselves are procedural with sort of different levels of textural impact. And so this is controlled, one, by the sort of top-down vertex color paints, but also with the curvature analysis, fall off. So that's a relative position to a camera. So this is for things like controlling sheen and aspects like that. And then another is thinking about the system of the volume of the material. So thinking about the subsurface properties. So in areas where the object is thin, I would place material which has subsurface properties which would allow more light to pass through versus areas which were sort of thicker or smoother, and I would make them sort of like a denser material to allow more light to scatter. The resulting properties from this allow a sort of smooth gradient, a real blending between the properties across the topology through to the sort of fine grain scale. And a particular challenge, typically in the representation of these objects, is that you would sort of box map and sort of fake the texture that's rolling over the surface, but this one is sort of unrolled at a consistent and uniform scale across that. So as you can see as well on the sort of the lighter areas, it allows more, so the thinner areas, more light is allowed to pass through and create these sorts of interesting sort of qualities. start to emerge from the overlap of these processes. So in the next stage of the development of this, I'm interested in pushing the topology, particularly in the reconnection of mesh topology as it combines and reforms. As in earlier experiments, through the remeshing process and recombination, it starts to further blur the lines between the qualities of these objects, but also allow the opportunity for the emergence of more unexpected qualities to occur. Thank you for listening to the presentation. If you're interested or in the types of work that we do, please make sure to check out the Tectonic Formation Lab Instagram, and so you can follow the QR codes on the screen. Thank you very much. So I'll pass this call back on to Da-Sung.
Mark, thank you very much. Thank you for sharing that. What is an incredibly thorough and sort of deep body of research. Mark's been working with us since the very first project in the lab back in 2013, working with us on and off, and really is leading the digital work in the lab, and so the digital research. So Mark, thank you very much for that. As you said, we'll now hand over to Da-Sung, who's going to discuss the work he's doing with primarily with machine learning and reinforcement learning. So Da-Sung, over to you.
Yeah, sure, thanks. I'll share my screen. Okay. Hello everyone, welcome all to our new workshop, and great honor for me as well to present in the digital future this year. Starting with some brief introduction of myself. My name is Da-Sung Wang. I'm doing PhD research in Tectonic Formation Lab supervised by Roland, and also Fabio Zambetta from Computer Science School as well. So my research is titled as Intuitive Agency, a heuristic approach for generative architecture design and robotic fabrication process. As a brief explanation of the title, the term intuitive agency consists of the agency of generative design and robotic fabrications, which speculates on a heuristic approach that augments existing design and fabrication process with artificial intuitions. The artificial intuitions are cultivated towards sophisticated and deep embedded architecture intentions through a self-training, learning, and incrementally evolving process, which can be inherited and adapted with generalizable applications. The highly experimental research topic aims to push the boundary of contemporary design and fabrication process towards a higher level of intelligence and sophistication with the implementation of machine learning techniques. The research is structured with three main tracks on generative systems and processes, machine learning techniques, and robotic fabrication processes. Starting with some reflections on the overall background, the research is embedded within a community of architects engaging with complex systems, generative design strategy, algorithmic techniques, and digital fabrications. The above several images are listed as purely generative research experiments from those architects, while the image below are some practical applications of those research. As some reflections of those algorithmic processes, two approaches can roughly categorize as parametric-based system or behavioral-based system. While both approaches are capable of compelling and sophisticated design outcomes, a series of limitations still exist as obstacle towards further development. Firstly, the parametric-based approach relies on the linear relationship between parameters and the system, which leads to generative outcomes that are limited to their predefined conditions. As for the behavioral-based system, as shown on the screen, it is a bottom-up generative process that analyzes complex system and self-organizing process, which has been widely developed as the basis for highly creative and voluntary design strategy, as explained by Roland. However, it's often limited by its logic of local interactions that resist encoding systematic and top-down design intentions. And in the field of architecture design, macro-level design logic plays a key role in the overall design process, which constrains its application in terms of more sophisticated design scenarios. Based on the reflection, the research speculates that a heuristic and top-down process as machine learning has potential to train the generative system with a higher level of intelligence and more global control. The discipline of architecture is rapidly absorbing machine learning methodologies and searching for its meaningful applications in the last several years. This diagram lists the number of machine learning research in architecture and categorized them into 3 frameworks: supervised learning, unsupervised learning, and reinforcement learning. Generally, majority of the research on machine learning in architecture is in the stage of exploring and experimenting, among which the research of applying GAN, which is and its associated algorithms on image generating and urban scale data analyzing counts for a significant percentage of total. Recently, the field of 3-dimensional form generating with machine learning has been gradually explored with some latest emerging research. The research starts with some basic understandings of 3 typical machine learning frameworks. Supervised learning is essentially an algorithm that trains a predictive model with a labeled datasets, while unsupervised learning is based on training a clustering or association model with non-labeled datasets. Both unsupervised learning and supervised learning relies on massive amount of existing data and directly extracts characters from them, which is also a major constraint on applying both frameworks on 3-dimensional form generation. In comparison, the mechanism of reinforcement learning can be summarized as an agent seeking an optimal policy by interacting with its environment through a feedback between observation states and quantified rewards. This means that reinforcement learning operates in a heuristic mode that involves itself through its self-exploration experiences with encoded intentions. So from a conceptual point of view, the research speculates that reinforcement learning has a stronger association with existing generative design process. As a similar heuristic approach, genetic algorithms or other similar evolutionary algorithms emphasize more on one-time optimal solution searching for individual case, while reinforcement learning tends to have adaptability to deal with more generalizable issues. Based on those studies, the research has a particular focus on exploring the potential of reinforcement learning. So the Intuitive Walk project is the first reinforcement learning-based design experiment I have done initially from 2018. The project aims to cultivate a random walk generative system with some artificial intuitions, which is extracted from the typical domino system by Le Corbusier. With the implementation of RL, it is expected that a posing character of random walk stochastic mechanism and the domino system's formality character can be integrated with a synthetic generative processes. Diving into some detailed definition of the experiment, the agent is an voxel that initially randomly moving towards 6 axes in a grid of fixed dimension. Some intentions extracted from the domino system as a training reward. So the first reward is layering space that agents will be charged when they form some floor space at certain heights. And the second reward is encoded based on intentions of spatial connectivity and habitations, which evaluates the spatial condition both horizontally and vertically based on each voxel. One of the training iterations has been quoted shown on the screen. So the left-hand side reward polyline chart shows the tendency of how the agent improves. And also from the right-hand side, we can observe from some of the training samples that the generative result evolves from like a solid piece at the beginning episode to form in later ones that starts to have some spatial characters similar as the domino system. The experiment has been further developed from a small, like a Wheeler scale, to a larger one, like a tower scale. So more tower-oriented design criteria are coded as a reward, including some structural logic and also some like a tower-oriented like height controlling as a reward. The further design experiment operates with a customized deep Q-learning framework with totally more than 10,000 training episodes. Overall, the character of form generated through those processes involved obviously over time creating a clear sequence of design intention. Overall, the character of form generated through the, so we can observe from the right-hand side that the character of form, so the system doesn't generate any effective intuitions at the first several episodes, but later on it starts to understand the predefined intentions as a tower type, and throughout the training process, the response to structural logic, some spatial connectivity and habitations are slowly improved, so becoming more and more obvious in the next several final episodes. So despite that all the rewards operate simultaneously, the process generated a multi-stage character that achieves one significant reward prior to addressing the others through a gradually process of improvement. Well, the generated samples has been selected and further designed through a series of algorithmic process as an explanation of how it habitates space and activities as a piece of architecture. The intuitive walk design experiment has been published in the proceedings of 2020 Digital Future Conference. So the intuitive walk case demonstrates the potential and capacity of combination of RL and generative design, but it is limited as its own generative logic and performance. So the research has been further developed with intention to hybridize the top-down RL approach with a bottom-up behavioral formation process. The second experimental project, Intuitive Behavior, exploring the synthetic generative process for pavilion-oriented criteria. Three major steps are structured to form the overall process. The first step, generative policy training, from the main step, which aims to train a generative system to achieve encoded global design intentions. And the second one, intuitive generating, is a step that a specific design context will be inputted to generate potential design outcomes. While in the behavioral formation, the selected outcome will be applied as a global topology to increase design complexities and resolutions. While the generating policy process, the RL agent is defined as a mesh graph that consists of certain vertices with predefined topology. As initialization of each training episode, the form of mesh graph and environment will be randomly generated in order to train the adaptability of the system. And in the experiment, the agent action is coded as a combination of stochastic RL actions and topological generative behaviors. In response to the technical character of RL observation states, the agent and environment will be converted into a computational field with a three-dimensional voxel grid. Each voxel contains informative states of the agent and environment. The states will be then calculated into a weighted value in order to structure a three-dimensional matrix for the artificial neural network to perceive. As the most critical elements of the training process, the reward is defined towards a global design intention of pavilion criteria. As shown in the diagram, three rewards are defined in this case. Spatial coverage is a criteria based on design intention of forming a mushroom-like topology. The design outcome is expected to generate a spatial coverage above a certain height, but remaining a minimum amount of foundation on the ground. Topological performance is defined based on the design intention of optimal structure topology. And the second environmental response is to train the system with adaptability within an unpredictable environment, which involves some obstacle avoidance. The RL-based training approach, the RL-based training process has been coded in animation. To the left above is the information of training episode and the rewards. The training process are shown in the left middle that mesh graph continuously makes generative decision to seek for an optimized topology, while the real-time state is formed into a voxel grid, feeding into the neural network. The left bottom is a polyline chart recording the average reward each 200 episodes. While in the red square, there are training samples randomly recorded every 200 episodes, and they are colorized from blue to red, representing poor to good generative performance. As the training proceeding, the reward value is significantly increasing with minor fluctuations. As more and more red samples are immersed on the right, which means that the system constantly evolves itself and behaves better and better towards the predefined global rewards. Zooming into two samples during the training process, the value towards three defined rewards, spatial coverage, topological performance, and set response has significantly improved respectively. By giving some specific site context, one of the samples has been selected within the generative pool and proceeded to the final behavioral formation process. As shown in the animation, the voxel has been converted into a series of plane cloud generated with random normals and directions, and the planes are then encoded with a number of local behaviors forming as the manifold swarm effect. When the planes has been formed into a more stable status, an body algorithm is implemented in order to increase the intricacy and materialize the form. So after a series of generative processes, the design prototype of an exterior pavilion has been visualized and shown in the on screen. So overall, the character of intricacy and emergence of a multi-agent system are integrated with the RL-based top-down global design strategy. So the research project of this intuitive behaviors has been published in the proceedings of 2021 KDRA conference with more technical details and further reflections. Then the research has been pushed forward towards some different branches. So this is an ongoing research titled as Intuitive Pro, which aims to increase the sophistication of generative process controlling with another typical self-organizing algorithm, the mesh growth system. I think Mark has mentioned this system a lot in the presentation. So the left diagram here demonstrates a more like a traditional generative system, like a simulation-based system. So basically, the diagram simplifies that most of the behaviors or parameters are implemented once at the beginning of the simulation process, and the form will evolve itself according to time with those static behaviors and parameters. However, so this diagram below speculates on a more intelligent and dynamic process that the system will constantly make decisions to implement different behaviors and parameters according to current condition of the form. So this represents a higher level of sophistication in controlling the form generating process. The red image is a prototype based on some sophisticated generative controlling with different combination of mesh growth behaviors. The intuitive growth experiment is based on a comprehensive study and development of a complex mesh growth generative system. So this diagram shows on the screen are the list behaviors developed based on some growth behaviors, which consist both they will split their faces when coming to some specific topology, and they can mirror their vertex and trying to grow from the naked edge. And several meshes when get close with each other, so they can re-merge itself like a manifold merge behaviors. So based on those behaviors, so based on the combination of different behaviors, the system is capable of with combination of different behaviors, the system is capable of generating various forms with distinguished generative geometry characters. The animation shows two typical growth methods. The left one is a mesh constantly split itself, and the right one is the mesh growing at the naked edge. So those generative system has been tested and applied in a number of parallel design projects and shown on the bottom of the diagram. And currently, the research in the process of integrating RL as an overall brain to control the complex generative system. So this is one of the definition of action, which using a grid to control a number of nodes to undertake actions lacking different growth behaviors and changing parameters. And so as some work in progress definition of using point cloud structure to represent a highly intricate form into a point cloud structure. And it is actually it's a huge technical challenge to represent a highly complex geometry with matrix datasets fitting into the machine learning framework. And these are some initial round training samples. So the project still work in progress with both some conceptual and technical constraints. But this shows great potential to enhance the generative process, especially with complex form generating systems. So another work in progress research direction is looking at training multiple agents collaborating with each other. So the previous experiments are all training the generative system as an entirety. But in this project, the research tends to train several components of the system to collaborate in order to be more adaptive. The shown image are some. So the shown image are some initial tests. So the first several tests are training several agents to respond and collaborate with each other. So the next several tests are trying to mimic the flocking simulation, but with reinforcement learning instead of local behaviors as the multi-agent system normally operates. So this branch of research is aimed to implement a multi-agent reinforcement learning framework, which is involve MADDPG algorithm to achieve multiple collaboration between agents. So as a further development, so this is another ongoing project proposal to push forward the experiment of intuitive behaviors. The design project will further develop the approach by increasing its scale and the functional complexity. The architectural topology logic and some macro level logic will be encoded as a reward to train the system. And some actual urban context will be integrated as test ground and demonstrates how the process will operate in a larger and complex scenario. So this is a combination of generative system machine learning, which is one significant part of my research. And another significant part is dealing with robotic fabrication process. So for instance, in the field of additive manufacturing, the robotic behaviors are normally based on direct programming going along a path from target to target. But when moving from a layered printing scenario, for instance, which shows on the left, but to some other printing behaviors like more spatial printing. So the controlling of robots starts to have some limitation in terms of some real-time response or some optimal design, optimal decision making. So we have proposed a robotic task shown in the left diagram. The robot expected to print onto complex printed object. So obviously it is very difficult to predict which are the paths that the robot is not able to reach, and also very hard to program the robot to make real-time decision to avoid colliding with the existing object. So the task has been simplified to train a robot moving from target A to target B with intuitions for optimal path to avoid obstacles. So in the diagram. So the research is work in progress in terms of tuning the definitions of actions and the rewards. And here are some early training tests that robots has started to behave intuitively, avoiding collisions, but the performance still underdeveloped into some more practical applications. So finally, as a conclusion, the intuitive agency approach shows a meaningful impact on augmenting generative systems with intuitive capacity and sophisticated control. The augmented approach to the application of machine learning techniques has been proposed with the intention to broaden the range and impact of AI application in architecture discipline. So the subsequent reflection of the research also anticipate an interactive correlation between designers and computational intelligence. So that's all for the presentation. Thank you all for your attention, and feel free to leave some comment and question. So if we still have in the following discussion sessions we have. So that's it.
Thank you very much. So those two presentations were very deliberately trying to show a very different relationship between multi-agent generative algorithms and their augmentation. And part of this is because we understand that multi-agent systems have this incredible generative capacity, but there's a whole lot of things that they're incapable of doing, which often have to do with what we describe as a type of global ignorance. And so multi-agent systems rely on this sort of series of local interactions in order to generate complexity and emergence. But there are some problems in architecture which are simply global problems. I mean, problems of structure or problems of enclosure are global. And of course, there's also different types of intention that operate within architecture. There can be intention which can be encoded at the bottom level, which is really about the relationship between individual parts or individual rules. But then there are also intentions which operate at a global scale, which have got to do with either they're to do with pragmatic concerns, some of the things that Dasong were talking about, or they've got to do with they might be highly esoteric aesthetic and formal concerns that Mark was talking about. And I guess these two approaches, you can see how we're using agent-based differential growth algorithms, one which is augmented through this constant feedback with Mark's hand, and the constant feedback with very specific top-down drawn gestural decision making. Whereas what Dasong's working on, of course, is a different type of top-down augmentation of these bottom-up systems. He's looking at how do you write the reward structure, sort of almost like a fitness criteria for what makes the output of these agent-based systems successful. And so as this work has sort of matured in the lab, these two different strategies have become sort of, I guess, highlights within the lab in terms of how we can begin to think about the augmentation of algorithmic approaches with a whole series of other concerns which the globally ignorant multi-agent algorithms aren't capable of dealing with independently. So I think, to me, that's sort of very, very, very important developments in terms of the computational work and the digital design work that's going on in the lab. I guess the other thing that I'd like to say about the work that Dasong's developing is there's obviously a lot of development of machine learning within architecture currently, but a lot of this is working on either existing data sets or generating their own data sets. And I guess our critique of that work is that inherently that means that the architecture you're producing is tied to its presets, tied to the already existing data sets. And so the approach that we're undertaking in the lab is to think about it differently and not to say, okay, can we use whether it's the 2D image work that's dominant within machine learning currently, or even like the sort of emerging 3D work with GANs, but instead saying, rather than sort of throw out the previous, I guess, research around generative design and try to replace it with what is a relatively simplistic tool, can we actually use machine learning to augment what's been happening with generative design and work out a way in which each of those two very different strategies, one that's working from the bottom up, one that's effectively working from the top down, how can they start to create a symbiotic relationship and create something which is greater than the capacity of either of those individual tools. So so Dasong, thank you very much for the kind of really detailed explanation of the work that you're doing. Okay, that brings to an end today's session. Tomorrow we'll have more researchers from the lab presenting work, and primarily that work will be around looking at issues around structure, issues of biological growth, and additive manufacturing. So I hope you can join us again for tomorrow's session. And with that, Mark, thank you very much. Dasong, thank you. And I hope to see you tomorrow. Good night.
Thanks.